Hey everybody, and welcome back to Calc 3 Online. So today I want to talk about curl and divergence, and I wanted you to watch this video after you watched 3 Blue 1 Brown's video on curl and divergence, because that video is going to do some more of the intuition, which I think can help like a ton here, whereas here I'm going to get into some of the more specifics of curl and divergence. So let's get into it. And I first want to just do another like line integral problem where we can use what I am affectionately calling Greenie Boys theorem. And so I'm going to always start off in any of these problems and figure out what region I'm talking about. So C is the boundary of the semi-annular region D in the upper half plane between the circles, blah, 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 and blah, blah, blah. Fancy way to basically say you've got a circle with radius 1, let's say it's that one, and then you got a circle of radius 2, you got that, C is the boundary of that whole thing there, so this thing right here. An annulus is like a donut, basically a two-dimensional donut, and so semi-annular is like a rainbow, like that. So we're talking. So if we do this as my direction, right? That will be my positive orientation, and it's going to be much easier to do the problem as like a integral over that region D, a double integral over that region D, because literally it would be 1, 2, 3, 4. Like line integrals I'd have to compute and then add together, and I don't want to do that. So this is 1, this is 2, that's going to be useful. My line integral here could reduce by Green's theorem to qx py dA, and then it's going to simplify actually really nice. So Q is right here, and so the partial of this with respect to partial of this with respect to x is 3y, and then the partial of this with respect to y is minus 2y, and then that would reduce, of course, to double integral just y dA. And so then it's not a simple type 1 or type 2 region, but I can definitely do a coordinate transformation to polar, right? And that would solve this thing out for us. So I'm going to do just r equals, not r, y, let's make that a y, equals r sine theta. That's really all I need, right? Because there's only y. And so then my double integral would become, I'm going 1 to 2, right, in the radius. I'm going 0 to pi in the angle. And then I've got r sine theta from the y, but I got an extra r dr d theta, well, an extra r, because of the Jacobian and the transformation from this place to this place now. And I'm not going to go through solving it. It's quite nice. It's all just nice, simple integrals, and we're kind of past the point where I'm going to explain all those things. You get 14/3. That's what the answer is. So that's just another example of how we can use greens to speed things up. I highly encourage you to go and spend some time and think about how to do this without Green's theorem. Not impossible at all, just really time-consuming and not something that I would want you to worry about. All right, so curl and divergence. These are just two operations done in vector calculus all the time, and I just want to show a little bit about how we do the actual computation of them, and talk a little bit more about the intuition, the idea, but that's really, I want to save that for the 3 Blue 1 Brown video I wanted you to watch, because he does an excellent job of like showing the visuals that I can't do and all sorts of stuff. So we're going to start off with curl. So curl is typically actually done in 3 dimensions, and it's a vector, just like this. So like at a point, you're going to get the curl of the field, at that point. Intuitively, it gives you a vector which measures the strength of the circulation at a point, okay? So it sort of measures the total push around the circle per unit area. You can think of it like in terms of whirlpools, like if there's not much current, the curl won't be much. If there's a lot of current, that vector will be longer or have a higher magnitude. That's kind of how you think of it. And, you know, there is a pretty messy computation here. I'm actually going to show you a much better way to do it, but this is what it is. Okay, so if you have PQR as a field, and you got your partials there, the curl is these weird subtractions in the different I and J and K components. I'm going to show you a little bit of a pattern, okay? In the I component, you'll never have in whatever component you're in, you never have that corresponding capital letter. So I, you don't have P. In J, you don't have Q. In K, you don't have R. Okay, that's one pattern to see. So I guess I can kind of show that like P only shows up in J and K, right? Another thing to see is that it typically goes the later letter minus the earlier letter. So R minus Q. I'm going to skip this one for a second. Q minus P. This one is different. Okay, it's doing P minus R. But one thing you're going to see is that there's actually a link here to a determinant. And so that term is negative, which is why the directions are changing. But typically, you get the later letter minus the earlier letter, okay? And really, I don't remember what these partials are. What I remember is the thing I'm going to show you on the next slide. So I'm going to kind of pause, because honestly, this is not how I think of curl. I'll show you a better way to think of it. There is two-dimensional curl, though. And just like with a lot of things in math, if your curl is, and this was in the 3 blue, 1 brown video, if you have two-dimensional curl going that way, so going counterclockwise, that curl there is positive curl. If you have curl going this way, okay, actually let me do some colors here, sorry. So let's say you got curl now going clockwise. That curl is negative, okay? And in 2 dimensions, curl is just going to give you Q with respect to X minus P with respect to Y. And this should look really familiar because it is greens. It's right here. We used it like right in there, right? Hopefully at this point you identify greens pretty fast. So there is a very big connection between the curl in greens, and I was talking about this when I first introduced it, and the actual curl that we're studying right now. Basically, we're talking about that circulation around a two-dimensional object, and showed in greens there's a connection between measuring the change of the field along that boundary, and turns out that that's the same as the double integral of that whole boundary. That's what green says, and so there is this curl connection to greens right here, so kind of interesting. But this is actually how I go about remembering how to compute curl, okay? It uses that, so this is what they call the Dell operator. We've seen it with the gradient. It just takes the partials of the respective components. So first one is partial with respect to X, partial with respect to Y, and so on, right? And this is that thing, it's actually called a nabla, is like the term. I think I talked about it when I introduced the gradient. Nabla is like Latin somehow for a like a harpsichord thing, or like whatever those are called. They kind of look like that. And so that's somehow the connection. But it is sometimes also called just the Dell operator. You see it a bunch in vector calculus. It's related to divergence as well, which we're going to see here in a bit. So this is actually how I think of curl, okay? So what I want to show you is I'm just going to literally do this Dell operator, which is just these weird partials, crossed with F, right, where it's PQR. It's a three-dimensional field, right? So if I do that out, I would have the following. All right, so let me try to explain my colors here. So the middle, like Dell vector line is all the blue stuff, right? And then this is green. And so I'm just doing, normal old determinant stuff. Determinant for the first component, you kind of blank those out, right? You do this times this minus this times this. So that's in here. And then I have a negative of the next determinant, right? Negative of this one. So this times this minus this times this. And so you can see, like, if you do for all three there, partial of r with respect to y minus partial of q with respect to z. And then this is the negative of that, right? So this is where the flip happens. You do partial of p with respect to z, right? Double negative, minus partial of r with respect to x, and so on. So these two things are actually the same. So this is how you should think of curl, okay? That's 3D curl. 2D curl is that Dell operator crossed with F. And so we're going to get I hat, J hat, K hat. And then we have partial with respect to X, partial. So we would have partial with respect to Y, and then we have nothing in K, and then we have P and Q, and nothing in R, 10. So now, if you do this thing out, if you look at what's going to happen here, when you do the blank out the first ones, you're going to get 0 minus 0, right? So you're going to get nothing there. Then you're going to do blank these out. You get this times this, nothing, minus nothing, right? So it's another 0. And then the last one, you're going to get partial of q with respect to x, right? So qx minus partial of p with respect to y. So you get p with respect to y. And so you can see that 2D curl is actually just the same thing as qx minus py in the k component, right? And that's, what greens is. That's just, greens is two-dimensional curl. Basically, it's like all your water is just flat on the surface, and you're just looking at it like these pictures, looking at it kind of top down, like that. So that's curl. That's how you compute it. We can just do a quick example here. So if this is my field and I wanted to find the curl, definitely the way I would do it is I would just set up del cross F. And so, you'd have this kind of thing. And if you do that out, the way I think through it is I basically look at this, and what I write down, so it's like I take the partial of r with respect to y, so that's going to be minus 2y, right? I'm just looking here, and then minus partial of q with respect to z, so minus xy, right? And then I move on to kind of blinking these out in my head, and I think, okay, I also do this, so I know it's going to be negative. So partial of r with respect to x, that's nothing, minus partial of z partial p with respect to z is x. And so then the last but not least, this is my 2D curl, q with respect to x, where is q with respect to x is y, z, and then minus p with respect to y is, there's no y's there, so it's 0. So then you get, you can't really simplify the first one, but we could call that second one x, and then y, z. And so what this is basically a vector, right, where now, like, you know, if you're at 3D space, you can just kind of be at any point you want. Like, let's say this is the point 1, 2, down in the X, and 1, 2, up in the Y. So this point is just like 2, 0, 2, or something like that. Now you can figure out at 2, 0, 2 in this field, what is the strength of the curl? Well, it would be, you know, -2 times nothing. Whoops, sorry, can't do the simple math. Minus nothing, and then comma 2, comma 0 times 2. So you would get nothing to nothing. And so that's just a vector which represents sort of the strength of like the circular movement per unit area at that spot. This stuff is used in like fluid flows and all the time, and fluid flows are a broad term. I feel like when I first heard that, I was thinking literally like water, and it can be water, but it can also be things like electric fields and stuff. So there's tons of things that can be understood as a fluid, and it's used all over the place in physics. So that's kind of the basics of how we find curl. For divergence, okay, pretty simple calculation here. So divergence is, we do write like div of f, basically, and it's literally just a sum of the partials of the corresponding components you're in. So p with respect to x plus q with respect to y, r with respect to z. And it is, if you think about it, right, this thing is basically a dot product of that partial with respect to x, partial with respect to y, partial with respect to z, this thing dotted with p, q, r. If you just dot those, right, we could write it this way, and that's what we mean by divergence, okay? This one's a dot product, so it's always going to give you a scalar, all right? And it's a scalar which basically measures how much stuff, and I'll explain this, leaves a spot or enters a spot in space, wherever you are. I actually was explained it with bananas years and years and years ago. But basically the way I've always thought about it is like you can measure the sort of import-export of goods, right? It doesn't have to be bananas, but you can sort of measure like, you know, bananas might be diverging from South America, and so there's a positive amount of bananas leaving South America, and then they might be imported to, I don't know, like Nebraska. And so there's actually a negative divergence in Nebraska because they're coming into Nebraska, right? The term is literally very logically defined. Like, if you take these two vector fields, okay, and the color doesn't show up too well, let's try blue. So if I take like a little like region here, this one, okay, has 0 divergence, because if you take any spot in here, just as much stuff kind of comes in as leaves, so there's 0 things net diverging from your little circle or whatever in space that you draw. Whereas here, right, this is like my, this is my beautiful picture of, I'm going to try and draw South America. Probably something like that. There's my Brazil. Boom. Okay. Kind of looks like Snoopy's head. But this is South America. And we got bananas leaving it. And this thing over here is Nebraska. I think that's how you spell it. I really can't read my handwriting. So Nebraska, where I'm importing bananas, right, would have a, this thing would have a negative divergence, because divergence because there are, an increase in the amount of bananas. But South America here would have a positive divergence because you have bananas diverging from that region. That's literally what it's measuring. So it's just a scalar, and in the 3 blue 1 brown video, he shows these nice pictures where as you move around in space, you can see like that scalar change. And so that's all it is. It's just a measurement of literally how much stuff in the field is leaving it or coming into it. It's kind of a measure of the sink or the source of the field. So maybe there's like, a lot of, you're talking about like the flow of electricity again, and you're leaving the one pole in the electric field and you're going to the other or something. Those can be sinks and sources. You can think of them. So you can talk about divergence at different spots in there. That's the idea. So pretty easy calculation with this one, and I feel like students don't struggle to memorize this one too much at all. You literally just do, it is del.f, but it works out to just the partials of, the respective things, like this one with respect to x, and this y, and this is z. So this is just like, I don't even need to write all that. So you just take the partial of this with respect to x, which is z. Then you would take partial of this with respect to y, which is x, z. And then this is nice because you take the partial with respect to z here, and there is no z, so it's just 0. And then just like before, now you have, this is not a vector. I knew something looked a little funny here. This one's a scalar. You're dot producting them, so you add all those things. So I add those together, and then you would get z plus xz. And now, like I was about to say, just like before, you can now take, you're at 2, over here at -1, and then you're down -2. So some point over here is 2, -1, -2. So then you can go up here and you can be like, okay, so my divergence at that point is -2 plus 2 times -2, which is equal to -6, right? And so since it is -6, right, that is like my Nebraska and my bananas analogy. So this represents a spot that is importing bananas, some product or whatever we're just going to call it. And it can be all sorts of different things, right? So there's an increase in stuff. There is not any amount of things diverging from that spot. That's the idea. All right, so I want to just finish this video up with like a few quick computations that are kind of nice. So this is actually a theorem that it actually shows up fairly often. So if f is a function of 3 variables, continuous second order partial derivatives, then the curl of the gradient of f, okay, so this is like the curl of a conservative vector field, right, is equal to 0. Okay, so that's basically what this is saying. It's saying the curl of a conservative vector field, right, one where this thing equals f, is 0. Conservative vector fields are ones like this, where it conserves the amount of stuff moving in and out, sort of a spot. And so to show that, to show that, we can just do like the definition of curl, which is this cross product. So we would do, here, I'll do it like this. So curl of the gradient vector field there would equal that gradient vector field. No, I want to do del crossed with that gradient vector field. That's how I want to do it. Just going back to like this definition, this is now gradient of f. So if I set that up, I would get this. And then I can just go and I can start doing the cross product out. And so if I do the first one out, I would get this. And you can see that just, this times this, you're going to get del squared f, but then you'll have partial of y, partial of z, right? And then you go minus this. And this is the cool little trick, right? So there's this theorem back, we learned it in like chapter 14, and I think it's spelled Clairaut's theorem is how I would guess to you spell that. But basically it said that, fxy equals fyx. So mixed partials are the same. That's what this theorem said. And so what you have happening here is you've got this these mixed partials that are the same, right? Y, z, z. So this whole thing actually goes to 0. And if you go through it, you're going to get that mixed partials in every component. So you're going to get a 0 in the j and a 0 in the k. And so that proves it. So if you just use Clairaut's theorem, then the curl ends up equaling literally just the 0 vector. And so what this really most often kind of is used for is that the curl of, so it basically says like if your field is conservative, then the curl is going to be 0. That's what it really would say. But yeah, the curl of a gradient vector field is 0. Just if you compute it out, you'll see it with the mixed partials. All right, one more thing here. I want to compute the divergence of the curl of f. So in symbols, anytime you see divergence, you're going to just do del dot, okay? And then curl is cross product. So you're going to have del dot del cross f. That's basically what you're being asked to compute here, okay? And so what I think I will do is I'm going to write down my curl, okay, which is this. And then the divergence, right, is the sum of those things with the partials factored in. So long story short, it basically will equal the partial of x with respect to that first component, and then plus the partial of y with respect to that second component, plus the partial of z with respect to that next one. And then what I think I'm just going to do is I'm going to highlight just a few of these. So if you look here and kind of here, like those two together, like you distribute this, you have partial of r with respect to xy, and then you have a minus partial of r with respect to yx. So that part will cancel out, right? And then you'll get, if you distribute this, but then you look at that one, right? You got an xz, a negative one, but then you got a positive xz. So everything literally there just cancels out. And so the divergence of the curl of the field equals 0. So the way I always intuitively thought of this is it's basically saying if you're curling around like this, right, there is nothing diverging from that situation, right? You're basically just going in a circle. You're not leaving the center or coming into the center or something. So when you do divergence of curl, there's nothing because intuitively you're just spinning around and spinning around and spinning around. You never leave the spot. That's how I always thought of it. But you can see it if you just crank through all the partials right there. So that is my quick kind of computation intro to curl. We will definitely do a lot more in the next few videos here.